Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So while talking about particle reinforced metal matrix composites, we started discussing about two very important things. One is weighting of particles and the other one is distribution of the particles in the final solidified composite. So in the previous lecture, we have seen that the distribution of particles depends on this parameter called alpha, which is the thermal conductivity ratio. The ratio of thermal conductivities of the particles and the metal. Okay. So depending on whether alpha is equal to 1, less than 1 or more than 1, the interface will take up a particular geometry. Okay. When it is alpha equal to 1, the isotherms are straight, and since the solid liquid interface also follows the isotherm of the melting point, it will also be straight, as you could see, without any curvature. Okay. So this will be a planar interface when alpha is equal to 1, and then when alpha deviates from 1, then the interface also gets deflected near the particle. Okay. If alpha is less than 1, then the interface develops a bump, as you could see from here. So the particles will tend to roll down over this bump, and this will lead to pushing of the particles, which will in turn lead to clustering. On the other hand, when alpha is greater than 1, then a trough is developed near the particle, and the interface can now engulf the particle, leading to uniform distribution inside the grains. And apart from this alpha, there is one more aspect that we considered, and that was the force acting on the particles. Okay. So the forces which act on the particles will also have a bearing on the distribution of the particles. So we have seen primarily there are three types of forces which act on a particle which is suspended in the liquid metal, and these are the gravitational force, which is due to the weight of the particle, that is mg. Then you have the drag force, which is due to the relative motion between the particle and the liquid metal, and then you have the force due to interfacial energy. Okay. So these are the three forces which act on a particle, and they also have a bearing on the distribution of the particles in the composite material. And how do they affect the distribution? All that we have already discussed in the previous class. And apart from these two aspects, it is also suggested that there is a critical velocity of the solidification front, which also has some effect on the distribution of particles. Okay. So it has been suggested that below the critical velocity of the solidification front, the particles will be pushed and therefore result in clustering, and above the critical velocity only the particles can be engulfed by the advancing interface, leading to a uniform distribution. Okay. Yeah, so there is a critical velocity of the solidification front. Which also has an influence on the distribution of particles. Right, so now that we have learned about the processing of metal matrix composites and also their characteristics in terms of the particle distribution, now it is time for us to have a look at the properties of metal matrix composites. Okay, but before that, let me also tell you what are the types of composites that you generally have, okay, in terms of the morphology of the reinforcement phase. Okay, so you can have, for example, fibers as the reinforcement. You can also have particles, and then you can also have short fibers or whiskers. So they have a particular geometry, right? And that might also have some effect on the mechanical properties. So a fiber reinforced composite is the one where you have aligned fibers as the reinforcement. Right, so all along the composite, you will have such fibers aligned in a particular direction. So this kind of fiber reinforced composites are also known as continuous reinforced composites or continuously reinforced composite, because the reinforcement here is a continuous fiber, right? On the other hand, you also have short fibers or whiskers, and then you also have particles. So you can have particles of different morphologies, size and shape. And such composites are also known as discontinuously reinforced composites. And then you also may have short fibers or whiskers, as I said. Right? So broadly, you can say these are the different types of composites in terms of the geometry of the reinforcement. So now when you talk about the properties of composite materials, the type of the reinforcement will also play a role, especially with this kind of fiber reinforced composites. Because here, since the fibers are aligned in a particular direction, depending on the direction of the loading with respect to the fiber alignment direction, the properties may change. Okay. So if you load in a particular direction, the properties that you get may be different from those when the loading direction is changed. Okay. So that kind of materials where the properties change depending on the direction of the loading are known as anisotropic. Right? Properties here are not same in all directions. This is because of the fact, as I said, that the fibers are aligned in a particular direction. Okay, it could be vertical, it could be opposite to that, or it could be in some angle also, right? But whatever it is, when you talk about the properties of a composite material, you always expect better properties compared to the individual constituents. Okay. So the objective here is to improve the properties. For example, when you talk about aluminum based composite materials, we look to increase the hardness and the strength of aluminum. Okay. So the properties should be a combination of both the phases, the matrix as well as the reinforcement. And this could be defined in a simple form or a rule which is known as rule of mixture, which basically gives you the properties as the weighted average of the properties of the constituents. Okay, so if you have two phases in a material, the properties will be combination of these two phases as the weighted average depending on the fraction of each of the phase. Okay, so in a composite material, let's say you talk about any property such as the elastic modulus, let's say, that will be a weighted average of the elastic modulus of the matrix and the reinforcement. So if Vf is the volume fraction of the fiber, let's say you are talking about a fiber reinforced composite over here, then the elastic modulus of the composite will be given by this as per the rule of mixture. F and M indicates fiber and matrix respectively. And Vf plus Vm is obviously equal to 1, right? So you can also write Vm in the form of Vf as well. So rule of mixture gives you a first-hand approximation of the properties of a composite material. Okay, and we are going to in fact prove this. So let us consider a fiber reinforced composite, and let's say it is loaded in the direction of the fibers. Okay, and the load is tensile in nature. So basically what we are saying is, if you have the fiber aligned in this direction, it is loaded parallel to the fibers in tension. And the assumption here would be is that the strengths in the fiber, in the matrix and in the composite are same. So that is the basic assumption which is made in this model to derive this rule of mixture. Okay. So a isostrain condition is assumed here. So this load P can be written as follows. Where A represents area. It is the cross-sectional area. And the composite strength sigma C will be given by the load divided by the area of the composite AC, where AC is the sum of AF and AM. Sigma C can be written as right. P is replaced by this. Okay. And now if you consider the length of the composite, this area fractions can be converted into volume fraction by multiplying the area with the length. For example, this AF by AC, if you consider this, both can be multiplied, both the denominator and the numerator can be multiplied by the length. So the numerator becomes the volume of fiber and the denominator is the volume of the composite. So this is basically the volume fraction of the fiber. Similarly, AM by AC will represent the volume fraction of the matrix. Okay. So from this, now we can rewrite this particular equation in terms of the volume fractions. Fm is equal to 1 minus Ff because the sum of these two is 1. So here we are actually dealing with the elastic behavior of the material. Since we are talking about the elastic modulus, so it is still in the elastic limit. And we have already assumed that the strains are equal. So within the elastic limit, we have the Hooke's law. So we can write the expressions for the corresponding stresses in the form of the Hooke's law. And therefore, the load in the composite now can be written as So from here we can write that and since these three are assumed to be equal, these three strands, we can write it as this one now. And we have already seen before that this area fraction actually represents the volume fraction. And therefore from here we can go to the expression which will represent the rule of mixtures. Right? So equation 1 now is the rule of mixture that we talked about, and this will give you the properties of the composite in terms of the combination of the properties of the individual phases present in the composite material. All right. So with that we come to the end of this lecture. Thank you for your attention.